Lesson 2 of electrical circuits is going to look at the components you need to be aware of. So you need to recognize the symbols when these crop up on circuit diagrams, but you also need to understand what they actually do as well. So there's lots of different components. Obviously, we're going to sort of restrict our learning to the ones that are relevant to the course, but just giving you an example of how many there are. And the complexity of some circuits can be very great. So this is a circuit board for an iPhone, and all the little segments in there are either individual components or processors. So obviously, the more that a device needs to do, the more components it requires, and the more complex that circuit becomes. So we're going to start with the most basic things. The first one being a cell and a battery. They are effectively the same, but when we're referring to a cell, we only have the single long and the single short line together. A typical cell has a value of 1.5 volts, although that is not a hard and fast rule. This is also an acceptable symbol for when you're drawing any circuit, because you can just annotate it with the voltage supplied. But strictly speaking, that is an individual cell. A battery is two or more cells combined. So you can see in this particular symbol, this would be an unknown battery because we use the dotted lines. If we wanted a 3-cell battery, we just have 3 series of a cell in a row. So over on the left here, we have typical AA batteries, which might have 1 or 2 cells. I should imagine, I haven't checked, but I should imagine they're an individual cell of 1.5 volts. But then this car battery would be a higher voltage, because you can see the caps on the top, they all link to an individual cell. So this car battery is actually a 6-cell battery. Now, the purpose of the battery is to supply the voltage. So without the battery, there's no push to make the current go round the circuit. So it supplies the voltage, which we can equate to being the push on electrons. And obviously, as we've talked about before, that voltage we can often refer to as the potential. So without the battery or without the cell, the electrons have no potential, and therefore they have no will to move around the circuit. The next one then is a switch. So a switch is a simple device used to create a break or to complete the circuit. Right, so this particular style would be an open switch. And for a closed switch, it's essentially that door in the middle completes the circuit so current can flow. So the purpose of these is basically when it's open, that circuit would be off because no current can flow because there's a gap. And when it's closed, the circuit becomes on because current can flow. And obviously that is beneficial because we can switch things on and off easily using a switch. Next one is a lamp or a bulb. This one also has a second, less commonly used symbol, where you have the circle and the Greek letter omega in there. Okay, so you might see this, but it is rarely used. The commonly used one for WJC exams is the X in a circle. So we have several types of bulb on show. You have your traditional bulb with the element or the filament going across from the prongs that I talked about when it came to resistance. So that is the very thin wire that generates a lot of resistance, and that's what generates the heat to make the gases inside the bulb actually glow. And then obviously we've got the more modern, more efficient designs as well on show. So the purpose of a light bulb or a lamp is to convert electrical energy into light. Right, this is his only job. As a side effect of that, we also get some heat being generated as waste. Okay, but there's a big focus on the course in terms of looking at devices in terms of efficiency. So that is one of the areas to focus on, is how much heat and light is actually generated by light bulbs. And obviously that idea can apply to a huge range of devices. Next, we're going to look at the resistors. Now, there's a range of resistors, and we're going to start with the most basic, but they all fundamentally act in the same way. So this is a fixed or ohmic resistor. The value of these never change, and they have that standard symbol of a rectangle. Okay, so whatever resistor goes into a circuit, no matter whether there's 1 amp or 100 amps going through it, the value of that resistor wouldn't change. So there's a huge amount of resistors because we need them for each value that's required. So you can see over here, I've got a diagram of some, and the bands on them would indicate the value of those resistors. Now that resistance is a fundamental quality of the material. The resistance is there even if the resistor isn't being used. So if a circuit is off, it still has resistance even though no current's flowing. It's a little bit like considering a knife being sharp. Even though you're not actually using it at the time, it still has that sharpness there. So the purpose of resistors is to slow down the current. They alter how much current is flowing, and in doing so, that also alters the voltage. So if you had a bulb in isolation, that would get all of the voltage as the current came through. So if we connect it to a 12-volt battery, because there's no resistors there to influence that current, all 12 volts should go to the bulb. However, if we add a resistor in there as well, that resistor would reduce the amount of current flowing in the circuit, but it would also take away some of that potential because the electrons have to push their way through the resistor. So if we had that set up on a 12-volt bulb, depending on the resistor, we might only have 10 volts on the bulb. So the bulb will become a lot less bright because now it's getting less current and less voltage. So therefore it's getting less energy per second, less watts. And obviously to keep it balanced, the lost voltage would need to go to the resistor. And that's part of the resistors generating heat. So as the electrons pass through the resistor, they create collisions that slow the electrons down, and then those electrons give up their potential, their voltage, as heat. Our next resistor is a variable resistor, and pretty self-explanatory. Unlike a fixed resistor, this one you can actually alter the value of the resistance that it shows inside the circuit. So a lot of the time these are used by engineers to actually design the circuits because you can keep changing the resistance until you get the effect that you want. So it's stuck with the standard rectangle symbol for a resistor, but we've also got this additional diagonal arrow going across it to indicate that it's variable. So anything with a rectangle is a resistor, anything with an arrow going across it would be variable. You can alter its settings. And you can see there's several different types for this. The one we're going to focus on is that one bottom right, the rheostat, because they're the ones that, should we ever return to school, that you'll be using. Now, the design of these is that they've got 3 inputs, 2 on the bottom and 1 at the top. And the design that we'd be interested in, because we don't want it to act as a rheostat, we want it as a variable resistor, we would have a connection at the top and then a connection at the bottom on the opposite side. And the way that these work are that we've got a nice low resistance bar across the top, so low ohms, and then we have a high resistance coil along the bottom. And we can choose when the current swaps from the bar to the coil. So the more bar it goes through, the easier the journey and the lower the resistance. The more coil it goes through, the higher the resistance because the journey becomes more difficult. And the way that we alter that is with this slider. So in this current picture, the electrons would flow that far along the bar, and then they would have to drop down into the coil, which winds round, so makes the journey much longer, much more difficult in a thin wire before coming out. So you'd get about 2/3 of the journey would be in low resistance, and then 1/3 of the journey would be in really high resistance. If we was to move that slider to the left and position it around here, that would give a much higher resistance journey, because now we've got much less bar to go through, and then very early on in the journey the electrons drop down into the high resistance coil, and they've got to go all the way around that coil before they can come out in the bottom right corner. So that's how we would alter it. Now, the purpose of these is to change the voltage and current settings within the circuit. So as I say, engineers would use that to help them design the circuit, make it function in the way they wanted to. So we can use this for our investigations. So any prac work for this particular unit would require a variable resistor for you to look how other components behave and to be able to take measurements. We would also use these in things like dimmer switches. So if we was to turn the lights down a bit, that's using a variable resistor. You would find them in fridges, ovens, anything with an adjustable setting. Volume control on a stereo or your phone, brightness on your phone would require a variable resistor as well. So anytime you see a scale where you've got a maximum and a minimum setting, there would normally be a variable resistor involved. The next one is a fuse. Now, fuses are really important because they do crop up in several topics on the course. If we start with the picture on the left, you can see there's several types moving from left to right. We've got a glass fuse, which is also the final one as well. They're generally found on the inside of appliances, and they don't usually get changed, but they're made with glass because the inside of a appliance requires very minimal voltage. So it's got very, very thin strands of wire, and we would need to be able to check whether those components are functioning correctly before they're fitted. The second one, we've then got a blade fuse. You normally find these in vehicles because they're quite thin and narrow and take up very little space because both contacts are at the bottom. So I'm sure if you root around inside your car, you can find the fuse box and have a look how they're fitted together. Obviously get permission before you do that. And then the third and the fourth one, there are more typical ceramic fuses, the sort that the course generally relates to. Now, the third one is marked up as 2.5 amps. So it's important to be aware that you can get fuses of any value, but for the purposes of the course, unless a question specifies, the only available values are 3, 5, and 13 amp. So unless you're told to pick from a selection, you would have to choose and know that the three available values are 3, 5, and 13 amp. And these are the values that you find inside plugs of the appliances around your home. And whenever we're doing calculations for a fuse, we would always calculate the current required by the appliance and then go one step up. So if it required 3.2 amps, you would still have to fit a 5 amp fuse in order for that circuit to work properly. Now, the symbol for this one is fairly intuitive in that it does pretty much look like the design of the appliance. We have the standard resistance rectangle because that's effectively what it is. And then it's literally the design. It has a wire going through the middle. So you can see on the ends of the caps of these three fuses is a little mark. That is the welding point for the fuse wire, which would run through the center of the fuse to the other cap. So that is essentially joining one cap to the other in order to complete the circuit. So these are always fitted on the live wire. So you have your live wire going into an appliance, then you fit your fuse, and it literally checks how much current is flowing. So if you have an appropriate amount of current, you would generate a small amount of heat because it's a resistor, and then it would go into the appliance, everything would work fine, and then that current would flow out through the neutral wire and back into your main circuit. However, if you had a situation where you had a power surge or too much current was flowing, or you fitted the wrong fuse that couldn't cope with the current that was flowing, that would mean that the wire inside would then be thinner. that would create more collisions, which would generate more resistance and more heat. So that fuse would get a lot hotter as more current flows through it. And eventually, if the current exceeds the set level, that wire will actually melt, and that would create a gap in the circuit, which would switch the circuit off. So the fuse is a safety device designed to measure or monitor the amount of current flowing, and if the current is too high, then it heats up and melts to create a gap in the circuit and shut it off before any damage is done to the appliance or anyone gets an electric shock. Okay, our penultimate resistor is a thermistor. So again, just to re-emphasize, we have this rectangular shape to emphasize that it's a resistor of some sort, and then we have this kind of squared off tick going across it. Now, these are resistors where it's not an ohmic resistor, and it's technically not a variable resistor, but the value of the resistance does change, and it changes with temperature. Okay, so the resistance of these alters as the temperature changes. Okay, and we can get them in two types. One where the resistance is proportional to the temperature. So as it gets hotter, the resistance would go up. So temperature along the bottom is our independent variable, and resistance up the side in ohms. So as the temperature increases, that resistance goes up and up and up. And we can also get them where the resistance would be inversely proportional to the temperature. So as the temperature goes up, the resistance would actually drop. So you'd find these in anything where you want to control the amount of electricity flowing based on temperature. So a typical example for this would be an oven or a fridge. Obviously, once a fridge gets down to the temperature you want it to be, you want it to shut off and stop getting colder and colder. Same with an oven. Once it reaches the temperature you've chosen to cook at, you don't want it still generating more and more and more heat. So you want it to shut off at that point. And then obviously as the oven loses heat, you want it to kick back in because that resistance has dropped again. Okay, so any time that we want a circuit to alter based on the temperature of that area, we would have a variable resistor. Another good example would be your thermostat. So you put the heating on, set it to 20 degrees, and once the room reaches 20 degrees, you want the heating to switch off, and that would be the job of a thermistor. A final resistor is an LDR, a light dependent resistor. And again, the description pretty much sums up what it does. The circle on these is pretty optional. Okay? You wouldn't necessarily lose a mark for not including the circle if you was drawing these in an exam. But you have the rectangle as usual to indicate it's a resistor, and these two arrows going onto it indicate light. And obviously because it's going onto the resistor, that light is coming from elsewhere. So these act in exactly the same way as a thermistor, but rather than temperature controlling it, it's the amount of light in that area. And again, you can have the two situations where the resistance can be proportional to the brightness. So as it gets brighter, that resistance would increase. But you can also have it that it's inversely proportional. So as it gets darker, the resistance would increase. Brightness along the bottom, because we could control that, we'll choose the settings, and resistance would be what we'd have to measure. So that would be our dependent variable at the side. Now, just like the thermistor is in any situation where we want the amount of electricity to alter based on temperature, this would be a situation where we want the amount of electricity to alter based on the amount of light. So you'd have this for things like security lights, where you only want them to come on when it's dark. You don't want your bright, very expensive security light running all day every time a cat wanders across the drive. You could also have it that you only want these things to come on when it gets brighter. So you could have these fitted in places like offices, where you want the monitors of TVs to only come on during daylight hours, because the chances are no one will be working at night, but most people clock off at 5 o'clock and don't bother switching their computer off. So it would be an effective way for companies to save money by making their equipment shut off when everyone goes home for the night. Our next couple of devices are diodes, two types of them. Now, a diode is a really important device because it's helped to miniaturize a lot of equipment from, if you was to Google mobile phones in the 80s and compare them to what they look like now. So they've been exceptionally important in miniaturizing technology to what it's like currently. Again, the symbol is pretty intuitive in terms of what it does. So we have an arrow flowing one way. Our next two devices are diodes. Now, diodes have been important in making technology much smaller over the last couple of decades. The symbol, again, is pretty intuitive in terms of what it does. So it comprises an arrow flowing one way and then a barrier from the other. And that is essentially what it does. It only allows current to flow in a single direction. Now, not that you need to know this, but it works by a combination of two semiconductors, where due to the nature of the semiconductors, you can only have electrons moving in that direction for the way I've drawn this symbol. So if current was flowing the other way, it wouldn't be able to move from this semiconductor to this one, so therefore no current would flow. Now, these are really important for anything that has very sensitive components that are likely to get damaged in it, because it means that the current can only flow in the correct manner. And you find these inside things that require batteries, and you know that because the batteries can only be fitted in a certain way. A bulb doesn't matter or doesn't care which way the current is flowing. If the current's flowing that way, the bulb will light. If you disconnected the battery or the power supply and put it in the other way, the bulb would still light. However, things like your TV remote, if you turn the batteries around, the remote no longer works, and that's because it's got lots of diodes inside there to protect all the systems and the setup of the circuit, because if the current was flowing through it in an incorrect order, it would damage the inside of your remote. Right? So the purpose of this is it only lets current flow one way. They're also really useful, again, in terms of miniaturization, because they work off an incredibly low voltage. So the graph for a diode would remain at the bottom initially, and then it moves up very quickly. So if you have very, very little voltage, you'd have no current flowing. But then you only need to apply around 1.6 volts in order to make the current start flowing. And you should notice that the graph goes up very, very quickly, which means that once you get to around 1.7 volts, which is still incredibly low, your system or your circuit is working at full capacity because it's allowing as much current to flow as is required. So this is why we can run things off very small batteries like AA. We might only need one or two to run quite a complex system. And our last individual component then is another diode. It's an LED, a light emitting diode. So again, the name's pretty indicative of what it does. So it's got the typical diode symbol showing that the current can only flow in one direction. But then again, it's got these arrows that indicate light. But unlike the LDR, the light dependent resistor, where the light needs to come from elsewhere, these arrows are moving away from the diode, indicating that it is the diode itself that's producing the light and giving it off. And I'm sure you're familiar with the diodes we have on the left, the sort of things you see at the top of a remote that indicate that the remote is still working. They're normally red. and we see these all over the place. So these are just a diode that produces light. Now, any of you that has a nice newish car, all nice cars now are fitted with LED headlights, because as I mentioned on the last slide, the fact that these run off incredibly low voltage means that you don't need much voltage, and when there's not much voltage, there's not much heat generated. So this goes back to our equation for resistance, R equals V over I. If the voltage is very, very low, so we've got a small number on the top there, it's very difficult to get a high number as your answer for resistance. So LEDs running off low voltage means that there's very little resistance, therefore there's very little heat generated, and therefore there's very little fatigue due to that heat on the inside and the workings of these LEDs. So the theory is that LEDs last forever. They don't break. Obviously, if you take a hammer and smash one, that will break it. But in terms of its normal functioning life of switching on and off, it should just work and work and work for far longer than that car would last, or whatever device it's attached to. So they're great in terms of the longevity of devices. It'll outlive bulbs by a long, long time. The downside, though, is that because they run off low voltages, they do tend to be quite small. So if you have a detailed look at the headlights of a new car, you'll be able to see the individual LEDs in there, and you need a lot of them in order to generate enough light in total for it to function as a bright headlight. That means that the initial headlight itself does become quite expensive, but it is a one-off purchase, and as long as you don't crash the car or someone deliberately damage your car, then you should only ever need one. Whereas in older cars, you need to regularly change your headlights, because not only do they break, but they also degrade over time and become more yellow, which means that they become useless and need altering or changing. So our last two to look at, not so much components, they are measuring devices. So these are things that we can add into a circuit, and they don't fundamentally alter what the circuit's doing. They're only there to give readings so that we can actually measure what the circuit's doing. So you could attach a bulb to a battery and the bulb might light up, which is great, but we don't actually know how much current flowing or how much voltage is being used by the bulb. So therefore we have to measure it. So this goes back to and links with our understanding of current. Whenever we're talking about current, we need to think about the electrons that are moving around the circuit. So our ammeter, the purpose of an ammeter is to measure the current in a circuit. Now, keeping this simple, we talked about that idea of electrons flowing around a circuit, losing their potential when they get to different components. And I did that as a straight line, looking at the potential at various points in lesson 1. We're going to look at a basic circuit here where it's just a cell or a battery connected to an individual bulb. So the current would flow out of that battery with its potential, go all the way around to the bulb, lose its potential in the bulb, which makes the bulb light up, and then returns to the battery with zero potential. Now, during that time, that current would be flowing. It's almost like an army of electrons marching. And it doesn't matter where you would position yourself, you would always be able to see the same amount of electrons. So an ammeter only needs to go an individual point in a circuit, because if you fitted one ammeter there and you fitted another one over here, the same number of electrons would go past, and therefore they would both give the same readings. So therefore, when we do this, because it's connected in one point, we say that these go in series, and they have to be fitted in series in order to function correctly. Another important pointer on these, not really part of the course, but just to help you understand why they don't actually alter the fundamental workings of the circuit, is that an ammeter is designed to have zero resistance. So you could literally fit 500 ammeters back to back in a circuit, and it wouldn't have any impact on the brightness of that bulb. Now, the diagram I've gone for, so you can see that it will take multiple measurements. This is an old analog milliammeter, and you can get various types of ammeters. And we do have these to be able to look at, but they're not really what we use nowadays. Obviously, technology has become better, and when you do experiments for this, you would use a multimeter. And so a multimeter can be set up as an ammeter, and obviously gives you a digital reading, so there's no ambiguity about what the actual value is, like there would be with reading a scale. And our last component is a voltmeter. So a voltmeter does exactly the same as an ammeter, but for volts. So it measures measures voltage. But again, we need to think about this in a sensible way. Now, we talked about voltage in lesson 1 as being potential, so how much potential an electron's got. But we also talked about the fact that we can't get hold of individual electrons to measure their potential. You can't just trap one and see how much energy it's got as it moves around a circuit. So if you remember from lesson 1, we talked about the idea that you have to look at that electron at one point and then look at it again at a different point to see what's happened to it. So this is where that term potential difference becomes key. And you have to have the word difference because we can't measure the individual potential because we can't trap those electrons. Now, to work out the difference, that requires 2 measurements. You need to know what the potential was before and what the potential was afterwards. So therefore, the voltmeter has got to be fitted in a different style to the ammeter, which can just go at one point. So if we had our bulb and we wanted to know how much voltage it was using, we would need to examine the electrons before they enter the bulb, and we'd need to re-examine those electrons once they have left the bulb. So our voltmeter would need to be connected to both sides of that bulb. And that's a term we call in parallel. And by doing that, we can measure the potential that the electrons have there. So we get a value for the voltage before the bulb, a value for the voltage after the bulb, and the voltmeter would display the difference. So if you had electrons going in with 12 volts, and let's say we had another bulb over there, so it's not going to 0, and they come out the other side of that bulb with 3 volts, then the voltmeter would do that calculation for you. They started with 12, they end up with 3, so therefore 9 have been used up from the first point to the second point, and therefore the bulb must be receiving 9 volts. And obviously that last 3 volts would go to the other bulb, so the electrons use all their potential before going back to the battery. Now, just like an ammeter going in a circuit doesn't fundamentally alter the function of the circuit, nor does the voltmeter. And the reason for that is that no current will actually flow through the voltmeter. All the current stays in that wire of the actual circuit. And the reason for that is that voltmeters have what we equate to be infinite resistance. So no electrons would choose to flow through the voltmeter because it's such a difficult path to go through, and they choose the lazy, much easier option of going through the bulb.